Hello, I welcome you all to your own channel MSK Learnium. Now in this class we are going to discuss about the simple Rankine cycle. So as you know, the steam power plant works on the Rankine cycles, or you can say the thermal power plant works on the Rankine cycle. So in any steam power plant, that main component of that part is that you have a boiler, turbine, condenser, pump. Obviously we have a generator is also, but as a mechanical point of view we will discuss only main four component, that is the boiler, turbine, condenser and pump. Means our work is that we have to generate the mechanical energy, means that whatever the heat energy is there, that heat energy is converted into the mechanical energy, or you can say the thermal energy is converted into the mechanical energy. So for that we require only four component: boiler, turbine, condenser and pump. So first of all we will see the schematic layout of a steam power plant, or you can say the simple Rankine cycle. So for a schematic diagram of any Rankine cycle, that is simple Rankine cycle, you can say here you have a boiler, right, and then turbine, that is steam turbine you can call it, it will be better, right, and next you have a condenser. Any type of condenser we can use, water cooled condenser or air cooled condenser. Here we have a pump, right. So this is what the arrangement will be like this, that is these are connected. So this is, and this like this, and this is like this from here to here, and again from here to here it is like this. Okay, so these are the direction of fluid at like this, like this, like this, like this, right. So here I am writing in short that B is the boiler, T turbine, C is the condenser and P is the pump, right. So now we can say this is the inlet of the pump, let's say this is the 1, right, exit of the inlet of the turbine, and this is the 2 is the exit of the turbine, or you can say the inlet of the condenser, this is the exit of the condenser, that is point 3, and you can say the inlet of the pump, and the point 4 is the exit of the pump or inlet of the boiler, right. In some cases we can take one more point here, O or something you can denote. Right now if the pressure and temperature while it is traveling from boiler to turbine, the pressure and temperature is varying then, but generally you can use this schematic layout and this notation right now. So first of all, as you know, then in a steam power plant, that is, or you can say in the Rankine cycle, the phase has changed, means the working fluid is not in a single phase, means the liquid is converted into vapor and vapor is converted into liquid. So first of all the liquid means water will be fed by the pump to the boiler. Here you have to supply the heat, right. So we are supplying the heat at constant pressure. When you supply the heat at constant pressure, it means that the temperature will be rise, right. So this high pressure, high temperature steam will enter into the turbine. It will be here the work is produced, right, and that means you can get the mechanical work we are getting, and the shaft will spin. Because of the spinning of the shaft, the EMF is produced and the electricity will be generated. What the turbine will do, that whatever the steam is enter into the turbine, that steam will be expanded partially, and the expansion will be reversible adiabatic expansion, or you can say isentropic expansion. After expansion, that the liquid and vapor mixture, that this region is the wet steam region, right, means it is the combination of liquid and vapor. So it will enter into the condenser. Here the heat will be rejected, heat is rejected, and then at a constant pressure only. So when the heat is rejected, it means condensation will take place. So whatever the vapor is enter into this partially expanded vapor steam, that will be condensed, and then the liquid is transformed. So this liquid is further fed to the pump, and then cycle will be repeated. So this is what you have a working mechanism, or you can say the working principle of a steam power plant or a simple Rankine cycle. So now we can see these things on PV, TS and HS diagram, right. So one by one we will see. First of all we'll try to draw, means we'll draw the TS diagram, that is temperature versus entropy diagram. So let's do that. Here we are drawing the temperature versus entropy diagram for the simple Rankine cycle, then the things will be very easy. So this is what we are taking, temperature on y-axis and entropy on the x-axis, right. So these are the DOM line we can draw, right? As you know, this is the saturated vapor line and this is the saturated liquid line. The point where the saturated vapor and liquid line are combining, means joining, that point we call it as a critical point, right? Now, so when, as you remember, that whenever the steam is enter into this turbine, right, so at the entrance of the turbine means, or the whatever the steam we are generating, that quality of steam we have a three types, means the steam will be dry saturated, steam will be the wet steam, and it is the superheated. So if it is the dry saturated, it means that this will be touches this saturated line. If it is the wet steam, it will come under this region. If it is superheated, it will come beyond this region. Means what? That you can say this is the pure vapor line, right? So if it is the dry saturated, the expansion means will be started from here. If it is the wet steam, means this is the region for liquid plus vapor, and this is the superheated region. So all three condition we will see. First of all, I'll draw the for dry and saturated, means that you have to assume that whatever the steam is coming from the boiler and it is entering into the turbine, that steam is dry and saturated. So first we'll draw dry and saturated steam. 1 to 2 expansion will take place in a turbine. This is 1 and this is the 2. And then this is the inlet of the turbine and this is the exit of the turbine, or you can say this is the inlet of the condenser. Now the condensation will take place and the whole vapor will convert it into liquid at the point 3, right? And after 3 you have to compress, means you have to pump the fluid to the boiler. So this is what 3 to 4 we are pumping, means work is supplied to the pump, and this is the isentropic compression, you can say. Again 4 to 1 we are supplying the heat at constant pressure. So this is what you have right now. So you can say expansion, heat is rejected here, and compression 3 to 4. 1 to 2 is the expansion, isentropic expansion. 2 to 3 heat rejection at constant pressure, and 3 to 4 we have a isentropic compression, means we are giving the work to the pump, and 4 to 1 we are supplying the heat in the boiler, so steam is generated. Now the first case I consider that at the means when the steam is entering into the turbine, that steam is dry and saturated. Now we see the wet steam. So for wet steam means this will come here, right? So it is like this, is it or not? That is 1 dash and this is the 2 dash, and the 2 dash to 3, that is condensation will take place. 3 to 4 compression, and 4 to 1 dash heat is supplied. Third, you can consider that suppose your steam is superheated. So when it is superheated, it means that it will goes beyond the line, right? So beyond the line means, let's say it is here, okay, so it will be like this, okay. So now you can say this is the 1 double dash and this will be the 2 double dash, right? And 2 double dash to 3 we have a condensation, 3 to 4 is the compression, and 4 to 1 double dash. First of all, whatever the steam is coming, that this you have to de-superheated, right? So this is the temperature is we are reducing. So 1 double dash, 2 double dash is the superheated condition. This is the temperature versus entropy diagram for the simple steam, simple Rankine cycle. Same thing we will see on the HS diagram. So before that, I will write down some process that you can say 1, 2, 3, 4, right? And 1. This is cyclic. That is means what? This is the for dry and saturated. For dry and saturated means what? The steam which is enter into the turbine, that is dry and saturated. So cyclic loop, that is 1. This is your 1, right? 1, 2, 3, 4, 1. Again 1 dash, 2 dash, 3, 4, 1 dash means what? This is for wet steam. If I say 1 double dash, 2 double dash, 3, 4, 1 double dash, it is the superheated. So it will be easy for you to understand. That is 1 dash, 2 dash, 3, 4 and 1 dash. This is for what? Which type of steam? That is for wet steam. For wet steam. For wet steam, right? And again you have a one more cycle we got, that is 1 double dash, 2 double dash, 3, 4 and again 1 double dash. That is cycle is there. So it is for superheated. For superheated, right? So whenever we have to identify the quality of steam, so the quality of steam we come to know from the dryness fraction, right? So in terms of the dryness fraction, as you know that if, or here itself I am writing, right, that is, this is, in this case is what, the dryness fraction is denoted by 1, x. So x is equal to 1, it is for dry and saturated. If x value is less than 1, means it is for the wettest steam, and if dryness fraction is greater than 1, that is x is greater than 1, it is the superheated, right? So these values, this is what we have seen, the temperature versus entropy diagram for the simple Rankine cycle. Now we will see the enthalpy and entropy diagram, right? So we can say enthalpy and entropy diagram, and then later on we'll discuss the processes. Okay, so first of all we will draw the HS diagram, that you can say enthalpy versus entropy diagram for simple Rankine cycle. So HS, enthalpy, entropy for simple Rankine cycle, right? For simple Rankine cycle. All right, now so we will do that. So here we have a enthalpy on y-axis and entropy on the x-axis, right? So this is our enthalpy, that is H, and this is our entropy, which is S, right? We need to draw the DOM line. So its DOM line will be like this. Wait, yes, right? So two constant pressure line we have to draw, means for one for boiler and one for the condenser. So let's say this is for boiler, right, and this will be for condenser, right? Same, you have a, first you have a expansion in a turbine, condensation in a condenser, compression in a pump, and heat supplied in a boiler, right? So three conditions we have to take, that quality of steam will be dry, saturated, wet steam, and superheated at the inlet of the turbine. Means when you are, means whatever the type, what type of steam you have generated in a boiler, maybe it will be dry saturated, it will be superheated, or wet steam. So all the things we'll see. So first of all we will see the dry saturated. Dry saturated means this is the, again you have a saturated vapor and this is the saturated liquid. So for this dry saturated, let's say it is like this, 1 2, here you have a 1 and this is the 2, right? And 2 to 3 you are condensation, that is, this is the 3. At the end of the condensation, means at the end of the condensation the fluid is a liquid state, right? And then you have a 3 to 4, that is compression, and 4 to 1 you have a heat is supplied in a boiler. So this is boiler, turbine, condenser, and pump. Now this 1 2 3 4 is for dry saturated. Let's say the steam is a wet steam. So for wet steam you can see this is 1 dash and 2 dash, simply 1 dash and 2 dash. This is the expansion in a turbine. At the end of the expansion it is the, sorry, at the inlet of the turbine it is the wet steam, so that's why it came here. So 2 dash to 3 condensation, 3 to 4 pump, and 4 to 1 dash is the heat supplied. Again this is the superheated. So for superheated it will be like this. Yes, so we can show here that, let's say this is superheated. So this is the 1 double dash and this is the 2 double dash. Okay, so this is how you have an enthalpy and entropy diagram for the simple Rankine cycle. Now we will see one by one what are the things. So I'll write on the process here, that you can make a point that or you can say the various process in simple Rankine cycle. So we can say various processes, okay, in simple Rankine cycle, in simple Rankine cycle, right? So first process we will see here, that is what, isentropic expansion in a turbine. So you can say 1 to 2 is the isentropic means reversible adiabatic expansion, right? So these are ideal condition I am taking. If I say irreversible adiabatic expansion, means this is the actual, right? So we are not discussing that actual, in ideal only we have seen the isentropic expansion, or its name also you can say reversible reversible, okay, adiabatic expansion, where you are expanding the fluid in turbine, right? Expansion of steam in turbine, right? In a turbine, right? In a turbine. So this is like this. Okay, now second is what? After expansion, this is what you have expanded 1 to 2. Now you have to condense. How? At constant pressure, right? So you can say here, just wait. Let me arrange this, right? So next you can write the next that is process which involved in a simple Rankine cycle is your, right? So this is what? 2 to 3. 2 to 3 is what? That constant pressure heat rejection. So we can say constant pressure, right? Heat rejection. Where you are rejecting the heat? You are rejecting the heat in condenser, or you can say the heat rejection in the condenser to convert condensate liquid, or you can say heat rejection in the this point you have to means it will be better if we will write right now in the condenser to convert what? Condensate, to convert condensate into water, right? Into water. Okay, let me do this one thing. Wait, why? Because its arrangement is right. Next we will see I'll show you. This is what 3 to 4 means. Again you have to compress. So compression is also isentropic, right? So you can write further that 3 to 4, right? What is 3 to 4? Isentropic compression or reversible adiabatic compression. Isentropic means entropy will be constant, right? Isentropic compression, or you can say this, that is reversible adiabatic what? Compression. Adiabatic compression. In where? At a low pressure, right? At a low pressure is pump, in a pump, right now. And then finally 4 to 1, that is 4 to 1 is what? Again you have to supply the heat to the in boiler to get a steam in a at constant pressure. You can say 4 to 1, that is constant pressure heat addition or heat supplied. Constant pressure, right? Constant pressure heat supply, where you are supplying heat supplied water to convert into steam, okay? Or you can say water is converted into steam, right? At constant pressure. Already we have discussed. Then now we see that we'll do the analysis of a Rankine cycle. Analysis of Rankine cycle in the sense that we are going to discuss that what is the performance, that how to get the thermal efficiency of a Rankine cycle, right? So thermal efficiency is nothing but the output by input, that you know, okay? So when you have to calculate the thermal efficiency of a Rankine cycle, it means that you have to calculate the output. Output is what? Net work, that is turbine work minus pump work, and input is the heat supplied, right? So you can write next the subheading, that is analysis of Rankine cycle, okay? So here we'll go, that is analysis Analysis of Rankine cycle, right? Rankine, actually, maybe there is a pronunciation mistake. Okay, Rankine cycle. So now first of all we will do the analysis for expansion, that is turbine. So you can say that 1 to 2 process isentropic expansion, right? Isentropic expansion. Okay, or in bracket you can write you are analyzing for turbine, right? You are analyzing for turbine. So turbine is what? Turbine is a turbo machine in which the hydraulic energy is converted into mechanical energy, right? So mechanical energy means what? That mainly the work is produced by the turbine. So how much work is produced by the turbine, that we will see. So turbine work, if you look at here, that any TS diagram or HS diagram you can say. So here you have your expansion. Let's say this is the dry and saturated. So here you have an enthalpy is H1 at this pressure, is it or not? At a boiler pressure, and this is the enthalpy 2 at a condensation pressure, right? So or pressure or temperature also you can take right now. So at that pressure, whatever the enthalpy value you got, and at a boiling means at a steam generation of means when you have steam generated in a boiler, what is the pressure of a steam, and then at the time of condensation whatever the pressure. So at that pressure we need to find out the enthalpy, means enthalpy value we can get from the steam table. So turbine work is what? That you can say turbine work WT is equal to H1 minus H2. That is H1 and H2 is nothing but the enthalpy. Enthalpy at the inlet of the turbine and enthalpy at the exit of the turbine. Okay, so here you can write H1 is enthalpy at inlet of turbine, right? And H2 is what? H2 is enthalpy at exit of turbine, right? At exit of turbine, right? And this H1 and H2 you can get from the steam table. So if you look at, either the steam is dry saturated or wet steam or the superheated, at the end it is wet steam. So H2 you can calculate from the formula, that H2 is equal to HF2, that is enthalpy of liquid at the pressure 2, means at condensation pressure, plus X2, that is in dryness fraction, means what is the quality of steam at the end of the expansion, into enthalpy of vaporization, that you can say HFG2, right? So this is the formula. By using this you can get the H2, and HF2 HFG2 value you can get from the steam table at a condensation pressure. So this is what you have an analysis of turbine. Next we will see the pump, right? Then you have a pump, that is you can say, sorry, next you have a 2 to 3, that is condensation. Here you can go 2 to 3 is the condensation, right? So condensation we can say that is heat rejection at constant pressure, right? So we can say 2 to 3, right? That is heat rejection at constant pressure, or that is the condenser, that is we are doing the analysis for condenser. How much heat is rejected we will see. So I'll show you that is what that means. Here from here to here the temperature we have to take Cp T2 minus T3, right? So you have a heat rejection is what? That you can say QR, that is heat rejection in condenser is nothing but H2 minus H3, that is enthalpy at 2 minus enthalpy at 3, right? Then again you have a 3 to 4, that is what? 3 to 4 is the compression work. So you can say 3 to 4, right? That is isentropic compression. 3 to 4 is the isentropic compression, right? Isentropic compression. Or you are doing the analysis for what? We are doing the analysis for pump, right? So pump work we have to see. Actually we are not, pump is not producing the work, we are supplying the work to the, means we are giving the work to the pump, right? So the pump work is negative actually. Why? Because work done in compression is negative, you know, in basics of thermodynamics. So here it is what the pump work is nothing but you have a H4 minus H3, you can see, right? So from 3 to 4 only, so that the pump work we can say WP is equal to H4 minus H3. H4 and H3 you can get from the steam table at a means at a leaving pressure of means at what pressure the pump fluid is leaving the pump and at what pressure fluid is entering into the pump, right? That you will get from the steam table. Again you can find the isentropic expression for work, that is here H4 you can get, that you can see if I write down the energy balance equation for the steady flow energy equation, that is what, this pump work is equal to what? Pump work is equal to actually you have a H4 minus H3, right? So H4 is equal to what? H3 plus pump work we can say. So you can get the H4 from here, the enthalpy at the end of the pump, right? That is H4 is equal to pump work plus H3. H3 you already calculated, that is how? That is enthalpy at the means exit of the condensation, right? Or at the exit of the condenser. Pump work you can calculate, that you can say isentropic work, the isentropic compression work, right? Isentropic compression work, right? So isentropic compression work is what? That is WP is equal to integration of P dV, right? Integration of P dV from where to where? From V1 to V2, sorry, P1 to P2, right? Or you can say Vf, that is specific volume of fluid, into P2 minus P1 minus P2, right? This value you will get. Sorry, this is P2 is lower and P1 is higher, right? So this is P1 minus P2, where Vp is the, Vf is the specific volume of liquid at condenser pressure. So here you can write that Vf is specific volume right, at what? Of liquid at constant, at condenser pressure, right? Next, then we have to finally find out the heat supplied, right? So heat we will supply in boiler, that is from 4 to 1, right? So next process we have a 4 to 1, that is what? Heat supply at constant pressure, right? So from where to where you are supplying the heat? You are supplying the heat from 4 to 1. So QS or Q addition, Q supply, you can say H1 minus H4, that is enthalpy at the inlet of the turbine minus enthalpy at the inlet of the boiler. Alright, so this is how we will see that what is the work in turbine, work in pump, heat rejection and heat supply. Now we have to find out the thermal efficiency, right? So you can say the thermal efficiency of simple Rankine cycle, thermal efficiency of simple Rankine cycle, right? Of simple Rankine cycle, right? Rankine cycle. So neta Rankine you can write that neta Rankine is equal to output by input, which is nothing but W net by heat supplied, right? So W net is what? that W net is turbine work. So neta rankine you can say, that is turbine work minus pump work by heat supplied. So what is the turbine work you have? That is turbine work you can say H1 minus H2, okay, and minus pump work we have calculated, that is isentropic work Vf into P1 minus P2, right, P1 minus, sorry, that is H1 minus H2 minus Vf into P1 minus P2 by heat supplied. Heat you are supplying from just now we have seen, that is H1 minus H4. So this is how we can get the neta rankine, right, neta rankine, okay now. So this is the efficiency of a Rankine cycle, that you can get H1 minus H2 minus Vf P1 minus P2, this is P1 minus P2 by H1 minus H4, okay. Next we can say in terms of the heat rejection, W net you can find like this also, that W net is equal to heat supplied minus heat rejection. This is also way you can get. So heat supplied is what? That is H1 minus H4, and the heat supplied is minus of H2 minus H3, right. So your efficiency of Rankine, that is neta rankine, is equal to heat work done by heat supplied, that is you can say heat supplied minus heat rejection by heat supplied, okay. So heat supplied cancel, means 1 minus heat rejection by heat supplied. So what is the heat rejection you have? 1 minus heat rejection is H2 minus H3 by H1 minus H4. In this way also you can get the efficiency of Rankine, right. So this is how we can see that how to get the performance of a Rankine cycle or performance of a simple power plant, right, which works on the Rankine cycle. So this is the main general formula, we will use this one, that is neta rankine is equal to H1 minus H2 minus Vf P1 minus P2 by H1 minus H4, okay. So now whatever the discussion we have did just now, based on that we'll see one numerical problem, then we can get the idea that how to find the efficiency and all those things. So one question on the screen, please write down, that is for a steam turbine Rankine, that means work on the Rankine cycle, enthalpy at inlet to turbine is 2800 kilojoule per kg, enthalpy at inlet to condenser 2061 kilojoule per kg, saturated liquid temperature or enthalpy at sink is 251.5 kilojoule per kg, and pump work is 2.5 kilojoule per kg, right. Find the heat rate in kilojoule per kilowatt hour. So when we have to calculate the heat rate, it means that we require the thermal efficiency, right. So heat rate is what? 3600 by thermal efficiency in terms of the kilojoule per kilowatt hour. First of all you have to calculate the thermal efficiency. Thermal efficiency means what? Net work by heat supply. So we can see, for better understanding, let's say it is dry and saturated, or it is wait, that is saturated liquid condensed, enthalpy of sink is 250 and work of pump is this one. Find the heat rate, right. So we can draw the one TS diagram for better understanding to this question. So let's say this is your temperature and this is your entropy. This is the temperature and this is the entropy, right. And then we draw the DOM line, right, and let's say this is your that superheated only, right. So this is 1 and this is the 2 actually you don't say that, why don't I write the 1 double dash 2 double dash, the why, because in one figure we have showed dry saturated, superheated, wet steam, that's why differentiation will make 1 dash 1 double dash, right. But when you draw only individual, you can do 1 to 2 only, right, 2 to 3, and then you have a 3 to 4 is pump work, and 4 to 1 we are supplying the heat, right. So this is 4 to 1, the flow direction is like this and like this, right. So the data is given. Let's say first is what? That enthalpy at the inlet of turbine. So 1 to 2 you have a turbine. I'll tell you that 1 to 2 is a turbine, 2 to 3 condenser, 3 to 4 pump, and 4 to 1 is boiler. So inlet of the turbine is this one, exit of the turbine is this, inlet of the pump is this, exit of the pump is this, or you can say the exit of the boiler is this one, inlet of the condenser is this one, and exit of the condenser, and this is the exit of the pump, right? So you can say that enthalpy at inlet to the turbine. Enthalpy at inlet to the turbine means what? This is the H1, right? Enthalpy at inlet to condenser. Inlet to condenser means H2, right? Saturated liquid temperature enthalpy at sink is 251.5 kilojoule, or pump work is given, right? So this is what enthalpy, saturated liquid temperature enthalpy at a sink. So sink temperature means what? That where you are rejecting the heat, you are rejecting the heat in condenser. So the enthalpy at the liquid means at this point the fluid is liquid, right? So this is the H3 is given right now. So now you can write given data, that solution given data, right? So what is the given data you have? That H1 is equal to 2800 kilojoule per kg, H2 that is enthalpy at inlet to condenser 2061 kilojoule per kg, and saturated liquid at temperature of enthalpy at sink, that is H3, condensate enthalpy is given 251.5 kilojoule per kg. And in the pump work, that WP is equal to 2.5 kilojoule per kg. In most of the calculation, while you calculate the net work, the turbine work minus pump work, right? So the pump work we are neglecting. Why? Because if you compare the values of pump work and turbine work, the pump work is very less, right? So most of the calculation we will neglect, right? So first of all, you need to find out what? That you don't have a H4, right? That is enthalpy at the end of the, means at the inlet of the boiler or at the exit of the pump, we don't have. So first of all, we will calculate the H4. So just now you know that H4 pump work is equal to what? Pump work is nothing but you have a H4 minus H3, right? H4 minus H3, or you can say H4 is equal to pump work plus H3. So pump work is how much? Pump work is 2.5 is given, 2.5 kilojoule per kg, plus H3 is 251.5. Alright, so what is that value? This is the 254 kilojoule per kg. We got that H1, H2, H3, H4. Now we can find the turbine work. So WT is equal to what? WT is from 1 to 2, means H1 minus H2. So you can say WT is equal to H1 minus H2. H1 is given 2800 and H2 is what? 2061. We got some value, that is 739 kilojoule per kg, right? Then you have to calculate the net work, that is W net is equal to what? Turbine work minus pump work. So how much it is? You can say turbine work is 739 minus 2.5. This, see how small value it is right now. So in most of the calculation we can neglect these values, right? So this we got 7, how much? 36.5, 736.5. The unit is kilojoule per kg, right? Now we need to find out the heat supplied. So where you are supplying the heat? You are supplying the heat from 4 to 1, means H1 minus H4, right? So you can say that heat supplied, right? So heat supplied is what? That QS is equal to H1 minus H4. Okay, so here only you can write H1 is what? 2800 minus H4 you calculated, which is 254. Okay, so this is 254. What is the value? 2546 kilojoule per kg. Now we need to find out the thermal efficiency. Alright, so we'll find out first thermal efficiency. Wait for a moment. Yes. So now we can find out the thermal efficiency. Just hold on, it's few minutes is there. So thermal efficiency you can find thermal efficiency, right? So neta TH is equal to W net by heat supplied. So W net is how much? We got the W net, the turbine work is 736.5 and the heat supplied is 24546. So we will substitute, that is 736.5 by 24546. 0.46, right? So you'll get the thermal efficiency, which is 0.2892, right? Or you can say 28.92 percentage. Then heat rate is what? That heat rate in kilojoule per kilowatt hour you have to calculate. Heat rate in what? In kilojoule per kilowatt hour. So the heat rate is equal to thermal 3600 by thermal efficiency. So it is what? 3600 by 0.2892. So heat rate we got 12445. So 12445 kilojoule per kilowatt hour. So this is the heat rate. Don't write the HR. Why? Because HR we already written in for the heat rejection. So this is how we will solve the problem related to the simple Rankine cycle, right? There are the method by which we can improve the performance of a Rankine cycle, that is the regeneration, reheating, that we will discuss in the next video. So please do like, subscribe, comment and share this channel. Thank you.